Yeah.
So whose day was that?
Right. Boots on the ground. Okay. I'm doing real work. Oh, I want to go into, I don't know. No, I want to get my bachelor's in engineering. So I'm sorry.
He works for an aerospace company, my friend, yeah. UTC Aerospace.
Oh, cool. I mean, like, ULA.
Yeah.
So I can imagine he's coming.
It's Lockheed Martin.
You're an adult.
Yeah, all right. Well, once you get the degree,
Y'all ready?
I'll read the next.
Taking it way back.
Yeah. No, don't be sorry.
No, not directly. Sometimes you simplify, sometimes it's one or the other, sometimes it's trig substitution, sometimes. So there was a question from 8.1, homework 8.1, number 6. Well, we can look it up too. So an idea was to take 9 minus 9x over this and multiply it by x squared over x squared. So that way we can get rid of that radical there. So we end up with 9x squared minus 9x cubed over x squared minus x. I haven't tried this route, but if you do this, then you're looking at an improper fraction, so you have to divide. The degree of the numerator is higher than the degree of the denominator. So you try long division from here.
So you higher than
Do what? Yeah, you could factor this. But still, you would have. You still have long division. Because one of the x's would go away. What if we factor the top? 9 times 1 minus x. Initially, maybe that doesn't look very helpful, but 1 minus x is a difference of squares. So can I write 1 minus x like that? Because this difference of squares is a plus b times a minus b that multiplies a squared minus b squared. So here's a 1 squared minus b square root of x squared. I think that's really the most efficient way to handle that. And then we can simplify this thing. And now we can just use the power rule to find the antiderivative. not a lot of simplifying you can do there, is it?
Let's just make u 1 plus root x.
Okay. So let's try u equals 1 plus the square root of x. And what does that make du? Okay, so that, I mean, initially, if you look at that, you may say there's an issue. I've got u, or 1 plus root x accounted for. So what I'm looking at is this. I need to account for the dx in terms of u. But I don't have a 1 over 2 root x to resubstitute for, right? And that's usually where we stop with u substitution. Well, it's not there. Can't do it. But that's not always the case.
So then once you just bring that 2 square root x to the u.
Okay, multiply both sides by 2 root x. How does that help? Say that again.
Just plug 2 root x u.
Yeah, but we can't. So we can't plug that in because you're mixing variables. I mean, we are going to plug this in, but as it stands, we can't have u's and x's with respect to u.
You solve the root of x and u minus 1.
Yeah. So this relationship here, our original substitution, tells us that if u is 1 plus root x, then u minus 1 is the square root of x. So that's what we're going to put in for that square root of x. Because we need everything in terms of u. Are there any questions on that? So then, we just end up with powers of u again. We should determine our balance as well.
It's 1 square.
Okay. See, where does that leave us? So we just powers of u and plug in our bounds. Or if you want to resubstitute and use 0.36 with the x, that's fine too. So this is a common thing that we see. You know, usually we're like reconciling with u's on one side and the dx on the other side, but this is still a valid thing to do. All we're looking for is something in terms of u when we make our u substitution. Any questions?
Then it would say, it sounds like pretty radical.
Yeah, it wants an exact answer.
Oh, exact answer.
Yeah. No, not at all.
Alright, so we have u to the 5 halves. That's 2/5 minus 2/3 u to the 3 halves. So basically, we just wanted an exact answer. Is that what it asked for? So that's 4. What is the square root of 7 to the 5th as an exact answer? Right, yeah, times 49 root 7. Just have the square root of 7 squared times 7 squared times 7. So that's 7, that's 7. Minus 1/3 square root of 7 cubed. And that's square root of 7. We got all of that stuff. Minus, we have here 3 over 15 minus 5 over 15.
7 root
7 root 7, yeah. No, because it's 7 squared gets pulled out. 1 7 left over. 7 root 7, thank you. And then we have, what here? Negative what? 3 minus 5 over 15. We'll just call that a plus. Plus. Unfortunately, the 4 out front's not going to help with any simplifying any of that, so I'm stuck. Yeah, so we can get them all over 15. I'm not sure what this is, but right like this.
I was like, I need a bigger mark.
Is that what exactly? Over 15, so 3. 15. So 3 times. We have it, right?
Yeah.
It's just going to be this radical with root 7 plus 2/15ths, whatever that is. 12 times 49. Yeah. Just combine these two terms with root 7 plus the 2/15ths.
Okay.
All right. Any other questions?
They said it, like on number 11, they used the use substitution, but I was wondering if there was like a faster or easier way.
Yeah, let's do that. Any other questions here with what we've done? Before we move on. Next question. Says you may use the method of completing the square to evaluate the integral. I mean, it's more than likely completing the square is just like half the battle here. So when we complete the square, what do we get?
What number is this?
Number 11. To complete the square on this. Take half of 2, just 1. Square it, add it here, subtract it here. that's, the method of completing the square didn't finish the problem. We still have to do stuff here. So we can try to split this up where it's 2x over all of this plus 1 over all of this. Or we could just try to go for a u substitution. So if u is x plus 1, then du is dx. So let's see what we've got here accounted for. It's just this squared plus 4. There's our u. We need to account for the 2x plus 1. So similar to that last problem, square root of 1 plus square root of x, that u plus 1, or u equals x plus 1, rather, we can solve for x. So x is really u minus 1. Bit better because we don't have the x plus 1, right? We just have the u squared. So I guess if it's better, it's a relative term. Yeah.
You need to put 64 up already?
Oh yeah, 64. Thank you. U squared plus 64 at the bottom. So on top you've got 2u minus 2 plus 1. Than our original integral, right? But we do have just a single variable here, u squared, as opposed to x, a quantity x plus 1 squared. So I don't know if that looks better or not. But here we are. So we don't need another u substitution if we split this up. Up, how do we evaluate the first antiderivative? Yeah. Yeah, so I mean technically there's a u sub involved here, but this is in log form already. The derivative of u squared plus 64 is 2u. So there's the function, there's its derivative. You could immediately take this into the natural log. Absolute value of u squared plus 64, but otherwise, yeah. That one. What about the second antiderivative? Yeah. Yeah. Specifically, this is arctangent of what? Your u substitution here, natural log, absolute value. U squared plus 64. So yeah, I guess technically 2 u substitutions, or 2 substitutions. Any questions on that one? squared was x plus 1. We'd have to be careful. That square is always going to be positive, but in this instance, we can't get rid of the absolute value. So where we left off, 8.2 integration by parts. Did this antiderivative of ln of x. Some of these, if you think about like the tabular integration thing we talked about, neither one of these two functions' derivatives will ever go away, right? So derivatives or antiderivatives of either the x and cosine, they would never go away. So when we see this integration by parts, what happens is we always end up with a comparable antiderivative. So let's maybe look at this, officially by integration by parts, and then if we want to, we can talk about it using tabular integration. So what should our u be equal to here? We got the trig function cosine x, which means dv. Remember, we choose the u and the dv. It's e to the x dx. So the derivative of u with respect to x is minus sine dx. And v is the antiderivative of e to the x. And so other types of integrals like this, it just, with practice, you start to recognize when you need to do this particular thing that we're going to do with this one. But for us, it shows up as a trig function times e to the x, or it could be like e to the 5x cosine of 2x, something like that. Okay, so the first round of integration by parts. We have u times v minus the integral of v du. Remember the whole thing with integration by parts, this integral of v du should be equivalent or less difficult or less complex than the original. So it looks comparable in difficulty. So that would suggest that we should try it again. Let's do it one more time and see what happens. I don't know if y'all like to leave the signs in there or not, or change them, but I'm going to change this to this. So more than once, just be careful of all your signs while you're breaking up. What we're breaking up now is this into two more pieces. This time we'll let u be sine and dv be e to the x dx. So du is cosine x dx. V is e integration by parts twice. UV. Minus the integral of V du. Okay, so what do we notice? Yeah, you're going in circles. But we're back where we started. We're back with an antiderivative we were trying to find originally. Anytime that happens, you can just solve for that antiderivative. So I don't know what this is because it's over here too, but let's put this thing over here with this thing. So we're going to add this expression to both sides of the equation. And that's true anytime you integrate by parts and you end up with the original expression again, you just put it on the other side with the other one, combine like integrals, I guess. So now on the left-hand side, now we have two of those things. All right, dx. Well, so we've got what two of those integrals are. We'll just divide by 2 and we have our result. Is everybody all right with this, where we're at right here? So we want to solve for that antiderivative, which means we just divide everything by 2.
That was clever.
Yeah, not bad. And then, of course, we have some final constant of integration after those two. I think oftentimes you see the e to the x and the 2 factored out. However you want to represent that, it doesn't matter. Anybody have any questions?
So if you did it with tabular integration, would you calculate?
Yeah, you would eventually, you'd have to stop when you noticed the same terms in the antiderivative, and you'd still have to solve for it. Yeah, you can certainly look at that. So we have our u's here and our dv's here. Our u was cosine, and our dv was e to the x. So with u, we take the derivative. So, I mean, we'll just do ... because this thing we would keep going. Also, don't forget to alternate signs if you're doing this. So this one's positive. We have to make this one negative. Positive. We have to make this one negative. And then antiderivatives, e to the x. So you keep going there as well. So we start here with dx. Yeah. And then notice if we went diagonally this way, we would say, okay, well now I've got a negative cosine times an e to the x. So you really do have to recognize, well, e to the x cosine x was the original antiderivative, so maybe I shouldn't multiply these things. This step doesn't need to be performed, because we recognize that's the thing we started with. So instead of going here and moving diagonally, we're going to take this and move horizontally and integrate that. So we have the integral of that instead over here. Let me put this up here. And then the same trick is utilized. You have to group those terms together and solve. So tabular integration, it's easier once you get the hang of it, but it's not a fail-safe. You still have to, in certain instances, you still have to know what you're looking for. Any questions on that? The table of integrals, you might see some reduction formulas, dealing with powers of x and exponentials, powers of x and trig functions. So there are reduction formulas for a lot of these things. Outside of tabular integration, example 9 would be a good use of a reduction formula. So when it asks us to verify this, or to justify why this antiderivative gives us this antiderivative, then integration by parts is used there because we see that's u times v, and this is minus an integral of v du. So we've got an algebraic and a trig function, or sorry, an algebraic and an exponential function. So we'll let u equal x to the n, dv equal e to the x dx. Okay, so du is n x to the n minus 1, and v is e to the x. So once we plug that in, that's our result. The antiderivative of x to the n e to the x dx is u times v minus the integral of v du. And there's the result. Since n is a constant, it's pulled out front. That's the result. Depending on the power here of n would determine how many more times we have to compute this integral. But then this integral, where it's x to the n minus 1 e to the x, well, that's still x to a power e to the x, so then this reduction formula is used again. Depending on how high the power, maybe it's used 3, 4, 5, 6 times. So do we want to evaluate this using the reduction formula just to see how it works? Or tabular integration would work really well here too. So the n is the power of x that we start with. So here in reduction formula with n equal to 3. It says that it's x to the third times e to the x minus 3 times the integral of x to 1 less power e to the x dx. same thing, reduction formula now n is equal to 2. So we have minus 3 times all of this. We're about to break this up into 2 other pieces. So just be careful because you have a negative 3 times both of those terms. Okay, so it's still x to the n, e to the x. So x to the n times e to the x minus the integral of x to 1 less power, e to the x dx. Oh yeah, 2 here. So then we do this one more time where n is equal to 1. We could multiply the negative 3 through all of that, 1 and 2. But that's the idea of reduction formulas. So it's x to the first, e to the x, minus the integral, e to the x dx. So here we would have x to the 0. So we get x to the cube e to the x, x to the third e to the x, 3x squared e to the x, plus 6x e to the x, minus 6 e to the x plus c. There's reduction formulas for like algebraic times a trig function too. And a what? A power? Well, no, it works. I think it'll work for trig functions too. Because eventually you'll get to an integral where you'll have something familiar like secant tangent or something like that. I guess they could be used there as well. And honestly, I think integration by parts and tabular integration is much easier than trying to remember all of these reduction formulas anyways. So, use your discretion. Any other questions about that? Okay, now the bulk of the work is done when we have to look at definite integrals. So this is how we're defining it. Remember the first UV can be evaluated immediately at the bounds A and B, but then we still have another antiderivative to take. So we can process it that way. And you'll end up like, let's say we have an expression like x e to the x from 0 to 1 minus the integral of e to the x from 0 to 1. That's kind of what we end up with when we do definite integrals with integration by parts. If you want to do these bounds separately, that's fine. I would just recommend that once we find the antiderivative of all of these things that show up, then just evaluate all of it from 0 to 1 or whatever. If you want to keep track of 2 different things, that's perfectly fine. x e to the 9x from 0 to 2. We'd let u be x, dv be e to the 9x dx. So du is dx. What's v? Okay, the antiderivative, so don't forget to divide by 9. So 1, we can have our u times v. And evaluate that from 0 to 2. And have the minus the integral of v du here. Or we could just work with the antiderivative until all antiderivatives are found, and then evaluate everything from 0 to 2. What's the antiderivative of this piece here? Yeah, 1 over 9 again, so we have minus 1 over 81. Or we could wait till we're done with the antiderivatives and just evaluate all of this at 0 to 2. Makes no difference. Yeah, so the disadvantage here is like if you had other common factors that you could take out and make simpler. If you're already figuring out what this value is, you're not going to see that, right? So I think the other advantage of just working this all the way through until all antiderivatives are done and then evaluating from A to B, you can make things a little bit easier. But right, they both share a constant of 1/9 that we can take out. And evaluate from 0 to 2. I mean, we could, but you still have to evaluate at 0 to 2, yeah. So we have to this. See how we can do that. But once we're there, that's it. You know, we hopefully know how to do that. I honestly don't care what route you're taking to do this. If you want to do, if you want to do the fundamental theorem of calculus twice at different times, that's fine. Or if you just want to do it all at once, that's also fine. So our exact answer is 17 over 81. E to the 18th is 1 over 81. Any questions? So again, the way we tell typically if we're going to use integration by parts is if we have the product of two functions. So keep that that in mind as you go through 8.1's homework, because a lot of those are use substitutions or simplify first, then use substitute. Try to keep the product thing with integration by parts in the back of your mind, because the more antiderivatives you see, you start to get a better feel of which method to use when. But we can look at this one. There aren't any inverse trig functions on your homework, but we can look at that. Yeah, I don't know. Did anyone get? I thought I took the last two examples out, but maybe not. Do y'all's notes index 11? Yeah. Okay. We'll end there as well. Okay. So what should our U be? U should be, well, remember the acronym? What comes before algebraic? Inverse. Or inverse secant. Remember the other, are you all okay if I use X's? I don't like Z's.
I don't like Z's.
Because my Z's end up looking like 2's, and then I have to put lines for my Z's. And it's just too many pen strokes. Okay. All right. X inverse secant of X dx. The other way to think about our acronym allowing us to pick what U is, on the flip side, is we can think about dV as being the largest portion of that integrand that we know how to take the antiderivative of. Right? So if we were to let dV equal to the inverse secant of X, do we know the antiderivative of that to give us V? No, we know the derivative of inverse secant, but we don't know the antiderivative. So there's a couple of ways to think about what we're choosing. All right, so then dV is X dx. The derivative of inverse secant. Anybody remember?
Yeah, square root of square minus x.
Yeah, which is what?
X squared plus 1. Minus 1.
Okay, minus 1 plus 1? Plus 5? Yeah, that's it. Yeah. No, X squared minus 1. All right, so can we leave or do we have to leave the absolute value in? Where is X in this problem? Yeah, between a positive value and a positive value. So X is always positive. We'll state that since X is in the interval from 2, 3 to 2. We don't need absolute values. If this were just inverse secant would be U, dV is dx. We could integrate by parts to find the antiderivative of all of our inverse trig functions. Well, I'm going to start down here. Run out of room. The integral is equal to x squared over 2 times inverse secant of x minus the integral of v d all antiderivatives, then we'll plug our bounds back in. So how do we integrate that? X over root x squared minus 1. Yeah, with u equal to, okay, x squared minus 1, yep. U substitution, u is x squared minus 1. So du is 2x dx. Our x dx is 1/2 we have the minus 1/2 here. Another 1/2 from our u substitution, du, and then it's u to the negative 1/2. Power rule. And we got our 1/4. Antiderivative of u to the negative 1/2 will give us what? No, that would be u to the negative 1. Yeah, 2 u to the positive 1/2. Alright, so we've got all this. Now notice we made a u substitution. Technically the bounds here would be different, but it's fine. We're in terms of x. We'll just plug back in for terms of x here and evaluate everything from root 2 over 3 to 2 and not worry about mixing u's and x's, changing bounds, different bounds here on this term versus the other term. Just keep everything consistent. U was x squared minus 1 to the 1/2. Okay. And now we've got our antiderivatives gone, then we can evaluate from 2 over 3 to 2. Do y'all have any questions on that?
Where did the negative
Where? This one? We have to add 1 divided by the result. So we have u to the 1/2 divided by 1/2. So it turns to the 2 u to the 1/2. Is anyone confused by that? Because we have different bounds, u's and x's. Is that okay how we're doing that? You have any questions about it? Okay, f of 2, we have 4 over 2. Inverse is secant of 2. We have 2 squared, 4 minus 1, 3 to the 1/2, 3 over 2. F of b minus f of a. So 2 root 3 squared, that's 4 over 3 times 2, that's 4 over 6. Does it really? I've seen me mess up like 15 times already. All right. Thank you for your faith in me. I appreciate it. Okay, inverse secant of 2. Do y'all have an inverse secant on your calculator? Anybody remember the relationship between the inverse trig functions and the reciprocals? So we know that secant is 1 over cosine. So the inverse secant we can write as the inverse cosine of what? Not 1. Okay, so it's the reciprocal. Inverse cosine of 1/2. This is the inverse cosine of root 3 over 2. Yeah, do you have an inverse cosine button? Okay. If you don't, hopefully you know that. Those are very common values. The cosine of what gives us 1/2? Yeah, so the inverse secant of 2 is pi over 3. And the cosine of what gives us root 3 over 2? Yeah, good, pi over 6. Okay. I mean, and then whatever, the rest is sort of numeric. 5 pi over 9 minus root 3 over 3. That's what you should get. Just want to make sure that everyone's okay with the process up to the point where we use the fundamental theorem. Are there any questions on the integration by parts and or the bounds? All right. In your homework for 8.2, you do also have a disc washer or shell problem. Because with these other integration techniques, we're expanding what we're able to integrate, right? So sometimes these like previous stuff will show back up. So in this homework, you do have volumes of solid. I think there's one question. All right, we'll take a break and then start 8.3. 8.3, we're looking at trig integrals, specific combination of trig integrals. So we'll see, we'll either be dealing with powers of sine, cosine by themselves, sine, cosine together, or tangent and secant, powers of tangent and secant together. Some identities to remember that will help you through. Some antiderivatives there. Before we actually talk about the strategies involved in integrating powers of sine and cosine, secant, tangent, we're going to look at the other 4 trig functions, the antiderivatives of these. A couple of them we already talked about. They're actually all, well, the first 2 are in log form, pretty much. The second 2 we have to manipulate by multiplying through by 1, and then they're in log form. So I think we did look at tangent and cotangent already, but we rewrite in terms of sine and cosine. And the derivative of cosine is negative sine. So we need, if that were negative sine, it would be in log form. If we're going to multiply by -1 there, we need to multiply by -1 somewhere else. So this is the negative natural log absolute value of cosine x. Let's see. Remember, all log form, antiderivatives can be evaluated by U substitution, where U is equal to the denominator. More commonly, we see the antiderivative of tangent as the ln of secant. But either will suffice. You do need to know all four of these too. Antiderivative of tangent, natural log the absolute value of secant. Cotangent, same way, we write that as cosine over sine. And since the derivative of sine is cosine, this is already in log form. So the antiderivative of cotangent is the natural log of sine. So for secant, you don't necessarily have to remember the derivation. Just remember what the antiderivative is. The form of 1 we multiply through by is secant plus tangent over secant plus tangent. Okay, that's going to force this to be in logarithmic form as well. Multiply through the numerator to the antiderivative of secant squared plus secant tangent all over secant plus tangent. And so looking at the denominator, what's the derivative of secant? Secant tangent plus the derivative of tangent, secant squared. So the derivative of the bottom function is now up top. So the antiderivative of secant is the natural log of absolute value secant plus tangent. And cosecant's similar. We're going to multiply through by cosecant plus cotangent over cosecant plus cotangent. Expand the numerator. Cosecant squared plus cosecant cotangent. So the derivative of cosecant is what? Yeah, negative cosecant cotangent. Derivative of cotangent, negative cosecant squared, right? So the function on the bottom, the derivative of this is up top, except for we're off by a factor of -1, right? We need both of these up top to be -1. So if we make have to have a -1 out here. We could have multiplied through by negative cosecant minus cotangent to get here as well. That's the idea. So you need to know all these antiderivatives now. Just what we've boxed in, not the, I mean, it's good to know the log form stuff, but what we've boxed in, you need to know. It shows up in this section, and it's even more heavily involved in 8.4. Any questions on this? So the power, powers of sine and cosine. So we have, the form is sine to the m, cosine to the n, and it says if we've got an odd power of sine and any power of cosine, whether it's even, odd, positive, negative, radical, whatever it is, just any real power of cosine, the process is to split off the sine x. Now you'll notice in all of these processes, it's except for the even powers of sine and cosine, the process is to split something off. You've got to know that the thing you split off lets you know what your u substitution is going to be. Because I guess in effect, the term we're splitting off is becoming like a dv, and that, or a du, and that tells us what our u substitution is going to be. So all of these are u substitutions, but we do have to split. Usually have to split something off in order to make that happen. So cosines to the 0th power is still a real number. So we have an odd power of sine. We need to split off a sine x. So we're going to split off a sine of x. And what we're splitting off, put with your differential dx. And that will always give, with these anyways, will always give us insight as to what our u substitution needs to be. So if this is, in effect, we'll see sometimes like this, there's a constant involved. So it's not always like a 1-to-1 ratio. This isn't always directly. But this gives us insight as to what our u substitution should be. And I think that maybe if we just remember what to split off, the rest of the stuff will make sense once we know what we're splitting off is telling us what we should make our u substitution. So our u substitution should be cosine, because the derivative of cosine is a negative sign, right? So if this is du, the antiderivative of sine is negative cosine, right? So we should allow u to be cosine, or you can let it be negative cosine if you want. That way our du is the piece we split off. Okay. All of the integrals we talk about, like I said, except for the even powers of sine and cosine, they all follow this a similar pattern. So then we can rewrite this. Sine squared, can't really do anything with, but we know sine x dx is negative du for this one. And what about this sine squared of x? Yeah, we go back to our u substitution. Our u was cosine, so I need this cosine, this sine in terms of cosine. So I just use the Pythagorean identity to rewrite that. We'll put our negative out here and our du. Okay, all right with that? Really, everything in this depends on what we split off. When we refer back to to our use substitution for the integral to determine what we have to rewrite. So now that's in terms of our use substitution. This is negative antiderivative of 1 minus u squared du. Odd powers of sine and cosine will be much easier than even powers of sine and cosine. Right. Any questions on this process? Yeah.
So like a reduction formula for powers of sine and cosine.
Yeah. There's a reduction formula for these. And then we're just integrating powers of u with respect to u. So we have u minus u cubed over 3 plus our constant, whatever. And u was what? Cosine. That's pretty much it. Once we've gotten the use substitution. Yeah, plus our c. In fact, if we have mixed powers of sine and cosine, and cosine's odd, it's the same process. You split off a cosine, let u equal sine, and then turn everything in terms of u. So notice very similar process. If cosine's odd and sine's any real number, then we take off one cosine, put it with the dx. That lets us know what our u substitution is going to be, and then all of the remaining powers of cosine get rewritten in terms of sine using that green identity. That works in a very similar way. We're going to just break off one cosine x, and put it with our dx. So that's kind of like our du right there. So our u substitution here should be u equals sine, and du is cosine x dx. So kind of a similar situation. The cosine x dx is our du. We need cosine squared in terms of u or in terms of sine x. We're going to rewrite cosine squared as 1 minus sine squared, which is do you have any questions about this? That's our antiderivative. Notice number 7 has both sine and cosine, but one of them is an odd power. So I'll try problem number 7. Everybody get the roll sheet.
Follow the day.
Okay, that's it. I saw most of y'all's, maybe one or two people were still working, but everyone else was able to get the correct answer, which is here. So, any questions on this? All right. So even powers of sine, cosine, or sine and cosine together. Yeah.
So since this one gives us the even, but I don't see if there's two odds, what happens if they're both odd? You just pick one?
Yeah, you can split off either or. So these, you just have to use those half-angle identities to rewrite. Okay, so these two. Let's go back one more. These two here. So those are what you need to utilize for antiderivatives. Of even powers of sine and or cosine. You just keep applying those. You get a square at a time. So with this one sine to the fourth, we're going to have to apply that identity two different times in order to integrate sine to the fourth. So the first thing we want to do is write this as sine squared squared. And then use the identity here. The identity there was 1/2. Let me do this. The identity was 1/2 1 minus cosine of 2x. So there's that sine squared squared. So now we have to expand 1 minus cosine 2x. So we got our 1/2 squared, it's a constant. And then we have 1 minus cosine of 2 squared. So 1 minus 2 cosine 2x plus cosine squared of 2x. Then we go back to the identity for cosine squared. We've got to rewrite that cosine squared of 2x as using that identity. So using the identity, what's cosine squared of 2x? Okay, close. The one we just utilized was for an argument of x. Now we have an argument of 2x. So it's going to be 1/2 times 1 plus. Well, if we write cosine of 2x, we haven't done our due diligence. Yeah, it's cosine of 4x, right? The angle is always double of what your original angle is. So we've got the cosine squared of 2x. What needs to go here is 2 times 2x. So we've got the 1/2 times 1 plus cosine of 4x. So now everything in the integrand we can integrate. times cosine to the fourth, then there's a lot more work to go through, right? You've got to expand those squares, then you got to multiply all that stuff together, perhaps use even or odd powers of sine and cosine. It get really, really difficult really quickly. Yeah, so here's, let's just kind of keep it safe here. We've got this 1/2, both of these. So let's just do it this way. Yeah. So we still have the original 1/4 that's up front. So let's just look at these as individual. We've got 1/4 times the antiderivative of 1 dx. The next one, we've got 1/4 times 2 cosine of 2x. So we'll just call that minus 1/2. Antiderivative of cosine of 2x. And we've got 1/4 integral times 1/2. So we've got 1/8 integral dx. And then 1/4 times 1/2. 1/8 antiderivative cosine of 4x. Okay, look all right. The antiderivatives then, antiderivative of this, we have 1/4 x. We got minus 1/2. What's the antiderivative of cosine 2x? Close. Sine 2x. Derivative we multiply by 2. Antiderivative we divide by 2. So 1/a sine of ax. We have plus our 1/8 x plus 1/8 antiderivative of cosine 4x sine 4x 4. This is times here too. Do you have any questions on this? So even powers of sine and or cosine, you just have to use those two reduction identities multiple times, depending on how high the even power is. So we have unlike terms here, because we have sine 2x over 4 plus sine 4x over 32. We've got 2/8 plus an 8. Any questions? Okay, how about this one? Number 9, cosine cubed of 7x sine negative 2 of 7x. What do we do here? All right, so yeah, be careful with these negative powers like this. There is room for confusion, because if I write this, what I mean is invert sine, right? Or arc sine. rewrite this,
One over.
right? Yeah, that's 1 over sine. So this is 1 over sine squared. We could write that as, say, cosecant, or when you have, you're saying you put the sine down here, then we have cosine over sine.
Yeah.
Yeah. So just be careful with the notation there. Yeah. Yeah, that, we might could try that, but notice cosine is even, or is odd. So since cosine's odd, we'll just split that off. Put that with a differential. So we're left over with cosine squared of 7x. So we should put a cosine 7x, and I totally ignored that. And this sine to whatever power, it doesn't matter. It's going to get taken care of with the u substitution. So what should our u be? U is the sine of 7x. That means du is the derivative of sine is cosine. The derivative we multiply by 7. 7 cosine 7x. We'll have that over here. So let's put that over here. So the thing we split off, 1/7 du is now that. Our u is sine of 7x. That takes care of the sine of -2. We need to take the cosine squared and rewrite that in terms of sine. So once we've done that, then our u substitution will take care of all of this stuff.
Don't want to use the number line.
For this one here?
Yeah.
No, so once we have odd powers, we split off one, you will be left with an even power. You can certainly use the identities used previous to, but that's going to make it more difficult. It's always easier to write those even powers left over from splitting off of an odd in terms of the Pythagorean identities. Because that's just 1 minus u squared now. And our cosine of 7x dx was 1/7 du. So once again, what we're looking at is just powers of u to find the antiderivative of 1/7 u to the -2 minus 1 du. So we have negative u that, or since this is 1 over sine of 7x, we can call that cosecant. Whatever you prefer, just don't confuse that with inverse sine. So, for this one, do y'all have any other questions on this one? Yeah.
So why did we think, since u to the negative 1 is just 1 over u, to make that natural log?
No, because we've already taken the antiderivative. It came from the antiderivative of u to the negative 2. Yeah, so from here, though, you could have written it as negative 1 over u, which is negative 1 over sine 7x. Okay, here's some reduction formula. There is no need to remember these. I mean, I guess you can if you want. But the methods we talked about in this section cover all of these for us, so, well, I guess maybe just except for secant and tangent, but. And again, just to see, get a feel for how it works, let's use reduction formula 3 with the antiderivative of tangent cube. So here, what they're calling n is equal to 3. So that's equal to tangent squared x over 2. Minus the integral of tangent to the 2 less, so minus the integral of tangent to the first dx. And notice that's as far as the reduction formula takes us. If we tried to use it here again on just the tangent, the formula says this is equal to this when n is not 1. So this is our n equals to 1 case right here. So now you got to remember, what is the antiderivative of tangent? Yeah, natural log of the absolute value of secant, or negative ln of cosine. Yeah, of cosine. So really, from here you've got two choices, because we saw there's two equal representations of the antiderivative of tangent 1. We could have tangent squared over 2 minus the natural log absolute secant of x. So that's fine. Or tangent squared over 2 plus the natural log absolute cosine. And the one absolute cosine is negative ln with this negative here goes away. Either one of those are valid for the overall integral. And if you look at the other reduction formulas, sine and cosine are fine because we know the antiderivative of those. But for secant, eventually you're going to get to a point where you have to integrate secant if you're using that reduction formula. Same thing, we could apply the reduction formula for secant cubed. Let's look at it in a different way just to give us some other techniques that we've looked at will also work. Secant cubed. Alright, let's to remember that there's a 12 multiplying, because we'll have quite a bit of work. You gotta remember to come back to the 12 and multiply it through. So here we're just gonna compute, let's look at the antiderivative of secant cubed as the antiderivative of secant squared times secant. And then we'll use integration by parts for this one. So this is kind of where the acronym fails, right? We have two trig functions. So the other way to think about it, instead of let u equal the leftmost function in that acronym, was to let dv be the largest portion of the integrand that we know how to integrate, right? So yeah, we know how to integrate secant. We also know how to integrate secant squared. So if we choose dv to be secant squared dx, that gives us more of the integrand, right? So we're going to let u equal to secant and dv equals secant squared, because we know the antiderivative of secant squared. Derivative of secant is secant tangent. And the antiderivative of secant squared is what? Yeah, tangent. Derivative of tangent secant squared. All right, so integration by parts tells us that this integral is now, just remove here, uv secant tangent minus the integral of v du. So minus the integral of secant tangent squared. Maybe after we do this, you might reevaluate whether you want to remember the reduction formulas. Okay, so this is where we're at. U substitution wouldn't work here, right? So from here, what we need to do is split this tangent squared in terms of secant, Pythagorean identity. 1 plus tangent squared, secant squared. Secant squared minus 1 secant. Secant tangent. Combine these. Secant cubed. Minus secant dx. Why would we do that? Yeah, because this is kind of like that e to the x cosine x antiderivative. We've got now a secant cubed here, and secant cubed was our original antiderivative. Just make sure you're keeping track of these signs. Yeah, so this is minus the integral of secant cubed dx. have minus minus, so I have plus the integral of secant x dx. Do we know the integral of secant? We had the secant cubed to the other side. But then that leaves us with integrating secant, which is why we talked about on the first page what the antiderivative of secant actually is. Right. Okay, so again, add the integral of secant cubed to both sides. So we end up with two of these now, two antiderivative secant cubed equals to secant times tangent plus the antiderivative of secant, which is natural log absolute value of secant plus tangent plus c, wherever that goes. Let's see. Yeah, well, once we know what secant, the antiderivative of secant cubed is, we'll go back with the 12. I mean, we could have carried the 12 all the way through, but it's just, yeah, there's already enough going on. Therefore, antiderivative of secant cubed. I don't know if you want to write both of these times 1/2, all of it over 2, whatever. Doesn't matter. Right, this is the antiderivative of secant cubed. Go way back up here and put that back in for this. Yeah, so we can say 12 to 6. Let's do it like this. Alright, good enough. That's 6 times all that. If you want to verify using a reduction formula, you can. You'll get the same result because secant cubed will have secant to the first tangent over 2, and then we'll end up integrating against secant here, ln absolute secant plus tangent. So feel free to verify if you want to do that. So that was the antiderivative of this right here.
Okay.
That's one of the ones we just have to know from the first page. Yeah. Good both. Okay. Next time we'll talk about the powers of secant and tangent and cosecant and cotangent. Have any questions before we go? Okay. See ya. Have a good weekend.